My name is myself K. Sirisha, working as assistant professor in MVR College of Engineering and Technology in Mechanical Engineering Department. Today, we are going to start a new topic. Now we are entering to third unit. So that is our topic is second law of thermodynamics. Now we are going to discuss about the topic of second law of thermodynamics and its basic concepts and statements. Okay, so first of all, before going to the second law of thermodynamics, first uh, we have to know of about the limitation of first law of thermodynamics. Already we know what is the first law of thermodynamics. First law of thermodynamics, also called as law of conservation of energy. That is the meaning of energy neither be created nor destroyed. So but it can transfer one form of energy to another form of energy. So in first law of thermodynamics, what it is says, the total energy is completely converted into total work done. So that is known as first law of thermodynamics. Here now we are discussing the topic of limitation of first law. So what is the limitation of first law? The first law of thermodynamics states that a certain energy flows takes place when a system undergoes a process or change of state is possible or not. So according to first law and cyclic process, work is completely converted into heat or heat is completely converted into work. So here the heat and work are mutually converted to each other. But from experience it is not true. So what it is says, so why you are using the mode of first limitation of first law? Actually first law is nothing but total work is converted into total work done. But in our experience, how it is possible total heat is converted into total work and total work is converted into total heat? It is not possible because of we are having some losses while we are doing the work into heat or heat into work. So it is not possible. But in our first law of thermodynamics, it doesn't any say it doesn't any say here. What it says, only heat is converted into work and work is converted into heat. So that is a limitation of first law of thermodynamics. And also one thing here also, uh, here also one thing, it is not, it doesn't tell any about the direction of heat, so how the heat is flow. So in second law of thermodynamics we can briefly discuss of about the direction of heat flow also. So the why you are because tell of about the limitation of first law is nothing but the first law of thermodynamics says that heat is complete. Heat is converted into work and work is converted into heat. That is the first law of thermodynamics. But in our experience, it is not possible. It is not possible. So that is the first law of thermodynamics. Limitation of first law of thermodynamics. It is not possible in our experience. So heat and work are heat is not completely changed into work and work is not completely changed into heat. So that is the limitation of first law of thermodynamics. Now we look at here once. So in limitation of first law, so another topic is, so first law does not help to predict whether the certain process is possible or not. Okay, the first law does not give information about direction and it does not provide and specify sufficient to condition to process takes place. So in first of thermodynamics, only says one thing is heat is converted into work and work is converted into heat. That is the only word it said about that. That is the first law of thermodynamics. But so here that word we taken into the form of limitation of first law. So first limitation is heat is converted into work and work is completely converted into heat is not possible. It by our experience it is not possible. So that is the limitation of first law of thermodynamics. And another limitation of first law of thermodynamics, where it is used and certain this process is, and that is the meaning of work is converted into heat and heat is converted into work. Is this process is applicable to any device, so it doesn't say so where it is uses and is this process applicable or not, so it doesn't any say, so that it fails. And first law of thermodynamics, it does not use about the information of direction of direction. That is how what is the meaning that here we take hot reservoir, here we take hot reservoir from to cold reservoir. For example, when we take a cup of hot coffee, then after some time it will be converted into cold because of hot is converted into cold. So we can say so, but we can say that because of we take one process, so it is definitely converted into cold. So we can say, but in first law of thermodynamics, it does not say when it is hot into cold and cold into hot, so the direction of heat flow does not it doesn't tell about the direction of heat flow also. So it is a limitation of first law of thermodynamics. And here we take first law of thermodynamics system. Here system, what is the first of them, when in system work is given to the system and gives the heat, otherwise heat is given to the system and so system gives the work. So that is only the process, it says the first law of thermodynamics, but it doesn't say how the heat flows from higher to lower or lower to higher. So it doesn't say anything of about that. So and it does not provide and specifies sufficient condition to process takes place, and it does not given the provide sufficient information about the process also. So that is the first for limitation of first law of thermodynamics. So what is first law of thermodynamics? So first law of thermodynamics is nothing but total heat is converted into work and total work is converted into heat. So that is the first law of thermodynamics. But why you taken limitation of first law of thermodynamics? Here it does not tell of about anything about the direction of heat flow. So whether it flows higher to lower, higher temperature to lower temperature, or lower temperature to higher temperature, and it does not give any information regarding the process also. Is this process possible or not? So those are all the terms we consider. It is a limitation of first law of thermodynamics. Okay, and next, second law of thermodynamics. So what is second law of thermodynamics? Okay, so what are the limitations we consider? That limitations we take and discuss about in discussed in second law of thermodynamics. So in second law of thermodynamics, what it says, the second law of thermodynamics, the second law of thermodynamics use more information about the thermodynamic process. So it gives more information about the thermodynamic process. And what the definition of second law? So heat cannot flow itself from colder body to a hotter body. Okay, the second law is also used to determine the theoretical limits for the performance of mostly used engineering systems like heat engines and heat pumps. So already told that in first law of thermodynamics, it doesn't give any information about so where is what is the process and what is the direction. It doesn't give information of first law of thermodynamics, but in second law of thermodynamics, it gives more information about the thermodynamic process. And also it said also one important main thing is heat cannot flow from colder to higher temperature, colder to hotter temperature. How it flows, it doesn't flow colder temperature to hotter temperature. And where it is used, the second law of thermodynamics. So and it is performed is mostly engineering systems like heat engines and heat pumps. So in second law of thermodynamics, we are used in heat engines and heat pumps. So very important, heat engines and heat pumps by using the second law of thermodynamics. Okay, and next topic is Kelvin Planck statement. So the Kelvin Planck statement is very important. So before going this Kelvin Planck statement, and we look at the diagram once. So what is the diagram? So what is the diagram here? Here this is the diagram. So already I told that second law of thermodynamics is used in engineering systems like heat engines and heat pumps. Okay, here look at here. So what the heat engine? doing the heat engine doing the process. So what is the heat engine doing the process? Like here, this temperature, this is the heat resource T1, this is the sink T2. So what is heat source? It has infinite amount of heat. It has infinite amount of heat taken from received. It has a infinitely amount of heat. We are heat received takes heat engine takes heat from heat source, but the temperature it maintains constant. The temperature does not change whenever the heat engine takes the amount of heat, but it does not changes it does not changes it temperature, like a sea, like a sea. If you take some amount of water in the sea, but it does change any, it does change any amount of water? No, because of it is a infinitely amount of water is there. If you are taken water, or for taken as a bucket of water, there is no any change. So that is the meaning of heat source. If you take certain amount of heat and given to the heat engine, but it does not change it itself, it maintains temperature constant. Okay, that we called as the heat source. And next thing, if we have taken a heat from heat source, and heat as input, as q is equal to 100 kilojoules, and this input is given to the heat engine, and it is doing some amount of work, that is w is equal to 40 kilojoule, and rejected amount of heat. So it takes from heat source and doing some work, and remaining heat, rejected heat, is given to the sink. So given to the sink also same like as a heat source, but in heat source we are taken, and the heat sink we are rejected, the rejected heat is supplied to the sink, like as a sea. If you uh, if you if you add a bucket of bucket amount of water, one bucket of water, is there any change in the sea? No, there it doesn't any change. So that is the meaning of that. It also maintains the constant temperature. So we are taken heat from heat source, and done some amount of work, and remaining rejected heat q is equal to 60 kilojoule. So we are taken absurd amount of heat. So the we are taken heat we called as heat source, and rejected heat we called as a sink T2. Okay. So here we called as absorbed heat. Here we called as a sink rejected heat. So Q is equal to 100 kilojoule, and doing some amount of work, W is equal to 40 kilojoule, and remaining heat rejected to the sink. So this is a total procedure for heat engine by using second law of thermodynamics. Why we are using the second law of thermodynamics? In first law of thermodynamics, we doesn't say heat flows from higher temperature to lower temperature. Okay, but in second law of thermodynamics, we strongly says here our heat engine takes heat from higher temperature and rejected heat to lower temperature. So we can say the direction of heat flow from higher temperature to lower temperature. So we strongly said it used your second law of thermodynamics. In first law of thermodynamics, we said we didn't say the direction of heat flow. It only says when q is converted into work and work is converted into heat. So that is the only thing it say. It says first law of thermodynamics. In second law of thermodynamics says about the direction also. So by using this second law of thermodynamics, we taking the engineering systems like a heat engine, heat engine, and heat pump and refrigerator. So here I will give the information of about the heat engine and the heat pump refrigerator. Now this is the procedure we called as the heat engine. So now we go to the Kelvin Planck statement. Sorry. So now we go to the Kelvin Planck. So this is the procedure for heat engine. This is the procedure for heat engine. So what is heat engine? It has taken heat from heat source and doing some work. The work is 40 kilojoules, and rejected heat sent to the sink, it is T2, but both are maintained. When it taken from taken from heat source, it doesn't change the temperature T1, and it added heat to the sink, and it doesn't change any temperature. The temperatures of both heat source and sink maintains a constant. Okay, now we go to the what is Kelvin Planck statement. Now we look at the Kelvin Planck statement. The Kelvin Planck statement of second law of thermodynamics is states that it is impossible it is impossible to for any device as heat engine that operates on a cycle to receive heat from a single reservoir and produce net amount of work. I will show that. I will show you. You can understand easily. Okay, this statement means that only part of the total heat absorbed by heat engine from higher temperature is converted to work. The remaining heat must be rejected to a lower temperature. Now look at the diagram. So here the higher temperature we called as a heat source and lower temperature we called as a sink. So T1 and T2. So heat flows from higher temperature to lower temperature. So this is the overall diagram of heat engine. But what the Kelvin Planck statements, so it said that here heat is taken from heat source. Okay, heat taken from heat source, Q is equal to 100 kilojoule, and it doing some amount of work, W is equal to 100 kilojoule, but it does not reject any amount of heat to the sink. It does not so directly Q is equal to 100 kilojoules, and Q is completely completely it will be converted into work. Is this possible? Because of any because of any no loss, the work is not 100%. So the here we look at heat engine as shown in figure 1 is converting 100% of heat into 100% of work. The system is not satisfying second law. Okay, what the second law says that heat taken from higher temperature and doing some work, higher temperature, heat taken from higher temperature, Q is equal to 100 kilojoule, and doing some amount of work, and remaining rejected heat given to the sink. So that is the second law of thermodynamics. But Kelvin Planck says that the heat taken from heat source as Q is equal to 100 kilojoule, and this complete amount of heat converted into complete amount of work. So when we take 100 kilojoule heat will be converted into 100 kilojoule of work without use any sink. So this system is not possible and does not satisfy the second law of thermodynamics. So this statement can be also expressed as no heat engine has 100% of thermal efficiency. How it possible? Because of some losses we get so that is the why for W is equal to 40 kilojoules. The remaining rejected heat given to the sink. But here the heat is completely converted into work without any losses, and it doesn't send any amount of rejected heat to the sink. It is not possible. We can run only take off heat source. So if you take design like that, we get the 100% efficiency, thermal efficiency. So 100% thermal efficiency is not possible. It is impossible. So this is our second law of thermodynamics, but it entirely different from second law of thermodynamics. So this diagram we called as Kelvin Planck statement. So this Kelvin Planck statement violates the second law of thermodynamics. Understand, students? So this diagram says that second law of thermodynamics, and this diagram says that Kelvin Planck statement. So this Kelvin Planck statement take heat from heat source and complete amount of heat converted into complete amount of work is not possible. It violates the second law of thermodynamics. So the Kelvin Planck statement violates the second law of thermodynamics. Okay, so Kelvin Planck statement violates the second law of thermodynamics. So this is the procedure for Kelvin Planck statement. Now we enter into the Clausius statement. Okay, now we enter into the Clausius statement. Same like as Clausius statement. same like as Clausius statement. So, sorry, Kelvin Planck statement. So, what the Clausius statement says? So, Clausius statement of second law of thermodynamics is as below. It is impossible to construct a device as heat pump to operate in a cycle and produces no effect other than the transfer of heat from lower temperature to higher temperature body. So this statement means that heat cannot flow from cold body to hot body without any work input. So when we look at the diagram once, we can easily understand. So this is here heat pump and refrigerator both are same, but the COP is different for both of them. So now look at the heat pump. We can observe one thing. So Kelvin Planck statement for we can observe one thing. Kelvin Planck statement for heat engine. Kelvin Planck statement for heat engine and Clausius statement is for heat pump and refrigerator. So you can understand students. So Kelvin Planck statement for heat engine and Clausius statement for heat pump and refrigerator. Now we look at the heat pump. Here look at once. Heat engine, the heat takes from higher temperature to lower temperature, but a small change for heat pump heat flow direction takes place from source sink to source. Now after this we will look at next, and first we look at this diagram first. Okay, so how the heat pump works, now we look at this diagram. Heat flows from lower temperature, so sink we call as lower temperature and heat source we call as higher temperature. So temperatures flows from higher temperature to lower temperature to higher temperature. But I want to give some example regarding of heat pump. So but when we look at the waterfalls, so waterfalls flows from higher body to lower body, but we could not use any external work to given to the waterfalls. It is natural, it is a naturally works high level to lower level. It automatically flows. We could not give any work to the waterfalls, but when we want to fill our water tank in third floor, is it possible to fill the water flows from the first floor to second floor? No, it is not possible. So what should we do? We will apply some amount of work was apply some amount of energy. So what type of energy would we will give to the pump? So that energy is nothing but electrical energy. So when we supply some amount of electricity to the motor, so that motor what it does, it flows the water from by using pipes and water given to the water tank. So when we want to supply amount of water to the water tank from lower to higher by using some amount of energy like electricity, at the same way here also when we are using a heat pump and refrigerator, it does not work automatically. We would give some amount of energy to the system, and it takes from lower body to higher body. So here we want to supply some amount of work to the heat pump. So it takes amount of work. So after that it flows heat from lower body to higher body. So that is the main reason behind difference between the heat engine and the heat sink and the refrigerator. Okay, here when we want to operate the heat pump, we have to supply some amount of external work to the heat pump. So then after it supplies heat from sink to source. So if you want the desired effect, we calculate the desired effect here in the sink only, okay. If you want to calculate the desired effect in sink only, if you replace heat pump with refrigerator, we will get a desired effect in sink. So the process are both are same, but the desired effect if you want heat pump in heat source, and if we want to get the desired effect for refrigerator in sink. For refrigerator desired effect is sink, For heat pump, desired effect is heat source. So what is finally we know that so in heat pump we want to run the heat pump. So the heat supply takes place from here heat sink to heat source, but we want to supply some amount of external work to the heat pump. So then after it will flows heat from heat sink to heat source. So that is the second law of thermodynamics. Second law of thermodynamics for a heat pump. Now we look at the Clausius statement. What the Clausius statement says that heat pump takes place from lower body to higher body, but without any external work. Is it possible, students? It will not flow cold body to higher body without external work. So it is impossible. So what the second law of thermodynamics? If you want to heat flow takes place from sink to source, we have to supply some amount of external work. It is possible for second law of thermodynamics for heat pump, but in Clausius statement it is using to run the heat pump, but without no external work from cold body to higher body. It is not possible. So the Clausius statement also violates the second law of thermodynamics. Okay, so Kelvin statement and Clausius statement both are violates the second law of thermodynamics. Okay, so this is the quotient of performance. Performance. How we take the coefficient of performance? So the COP is nothing but coefficient of performance. So coefficient of performance, which means that COP is equal to desired effect by work done. So I have already I have done already have said that so what is COP? Here in heat pump we have the desired effect in heat source. If we want to replace heat pump with refrigerator, we get the desired effect in sink. Now we are going to calculate the COP for a heat pump. So what is the desired effect of COP for heat pump? So COP is equal to desired effect to work done. So in a heat pump, when we will get the desired effect, so we will get the desired effect in heat source, that is T1. So in T1, what is the amount of heat supplied here? Q1 is equal to 100 kilojoule heat supplied. So desired effect is nothing but heat supplied for heat source. So Q1, so Q1 by what is the work done here? 40. So 100 by 40 is equal to 2.5. So coefficient of performance for heat pump is 2.5. Okay, so in other simple words, this statement can be defined as heat cannot itself flow from a colder body to a hot body. So what it says, Clausius statement, so heat cannot itself flow from cold body to higher body. Oh, is it possible? It is not possible. Okay, and next go to another topic. So we have the comparison between the Kelvin Planck statement and Clausius statement. So it is applied to heat engine. Kelvin Planck statement is applied to heat engine, and Clausius statement, so it is applied to heat pump and refrigeration. So Clausius statement is applied to heat pump and refrigeration. It is a negative statement for Kelvin Planck statement because of it violates the second law of thermodynamics. That is why we called as it is a negative statement. It is also a negative statement. It is also a negative statement because of it is also violates the second law of thermodynamics. Now we are going to the third point. It is based on experimental observations and no mathematical proof. So it has no any mathematical proof. It based only upon the experimental observations. Here also the same thing we talk of about in Clausius statement also. It is based on experimental observations and no mathematical proof. So those two terms here comparison between both of them. So this is the comparison between the Kelvin Planck statement and Clausius statement. Now we are going to the another topic. So what is our another topic is perpetual motion mission. Okay, perpetual motion mission for second kind. So in our already we have discussed in perpetual motion mission of first kind and first law of thermodynamics. What is the perpetual motion of perpetual motion machine of first kind. So without any external work, it can without using any petrol, but it run the engine continuously without any losses. So that is the example for perpetual motion machine of first kind, without give any work, but the engine runs continuously, so we cannot supply any amount of fuel to the petrol, sorry, to our bike, but it runs continuously. How it possible? It is not possible. So the perpetual motion machine is called, that is called the perpetual motion machine of first kind. Now we are discuss of about the perpetual motion machine of second kind. So what is the perpetual motion machine second kind? So here the thermal reservoir Q1, and this is the heat engine, and this is the W1. Here, if the engine exchange heat only single thermal reservoir. Actually, in cycle of thermodynamics, using the engine systems, sorry, using the engine systems like heat source and sink, but perpetual motion machine says it is using only the single thermal energy reservoir. Okay, so if you're using single thermal energy reservoir, it gives 100% thermal efficiency, so that is called the perpetual motion machine of second kind. So if the engine exchange heat only single thermal reservoir, in which heat is supplied is completely converted into equivalent amount of work, like a Kelvin Planck statement. So the Kelvin Planck statement takes in the form of perpetual motion machine of first kind. Okay, so we here in perpetual motion machine of second kind, sorry, perpetual motion machine of second kind, here we are using only one single thermal reservoir, and it gives 100% of heat supply to will be converted into work, and it gives 100% thermal efficiency. This processor we called as a perpetual motion machine of a second kind. Okay, so those are all the topics. So what is first law of thermodynamics? Heat is converted into work. So what are the limitations of first law of thermodynamics and first law of thermodynamics? Here it does not say any is the process possible or not, and it does not say any direction of heat flow, and it does not say any what is the systems it is used. So those are all we considered as the first limitations of first law of thermodynamics. So what is second law of thermodynamics? In second law of thermodynamics, so in second law of thermodynamics, it says how the heat flows from higher body to lower body, and how the cold body flows from how lower body to higher body. It says everything in second law of thermodynamics, and a brief description given in second law of thermodynamics, and it was it you and it says of about the Kelvin Planck statement, and it says of about the Clausius statement, and says of uh, about the perpetual motion machine of second one. So those are all the introduction parts for third unit. Now the next class we are discuss some more topics. I hope you understand, students. Thank you.